So in my last video, I made this 4-bit core rope memory circuit. This is a form of ROM that uses ferrite cores with copper wire that's wound, in this case, 20 times around it, and a high-frequency AC signal is passed through it to ground in order to induce an electric signal in the copper wire. And this was my schematic from the previous circuit. And what it essentially encompassed was a hex or a Schmitt-Trigger inverter as the high frequency fast oscillator. And that signal was controlled by transistors, which were switched off and on by an external signal, and the output of the transistor was passed into or not through various ferrite cores, and the output signal of which was amplified out with a op-amp comparator circuit. So, since I made 4 bits, let's make 8, and I put it on a piece of wood here and a perf board, and I made this with 8 address lines to start. So for the ultimate proof of concept, I wanted to use the 8-bit version of this to make a 7-segment display driver. A 7-segment display driver, as you can see here, each segment is controlled by a different bit of data, and each address controls those bits by putting a wire into and out of the appropriate ferrite core. As you can see, the number 0 has segments A, B, C, D, E, F. Segment 1 has excludes segment A, but includes B, C, and so on and so forth. You can see the number 2 here, how it's wired together, number 3, and this goes on and on until the number 7. Since I only have 8 address lines here, I could only go from 0 to 7, but you can wire any number together you want just by weaving it through the various ferrite cores. So you can see the proof of concept here. And now the number 7 is shown here, and afterward, this is the complete schematic of all of them, obviously, and I'm going to try and test this circuit out and see how it works in practice. So we're going to test out the first of these wires that's woven through. And it's got these skipping the first 2, it's got these last 6, and it's going to ground. So I have the output wired to this 7-segment display. So if I hit the first number, which is this black wire here, I should see a number light up. That's a 0. And I just gotta get the other 8 through there, or the other 7. With a tangled web, we start weaving. And we're trying to hardwire the code. Now I see how this was such a challenge. So I did the first 4 values here, and let's test it out here. 0, 1, 2, 3. Hardwired lookup table. It's a ROM that drives a 7-segment display at the moment. This is just for proof of concept. Now it looks extra tangled. I wired up the first 8 digits from 0 to 7. So now let's test it out on this. And let's look at it. 0, 1, 2, 3, 4, 5, 6, 7. Alright, so now I have this core rope memory circuit, and I have the address line inputs attached to this CD4017, and the outputs attached to this 7-segment display. So right now it's reading 7 because I wired these backwards. Here's my button clock. Now you could use this core rope memory as a proof of concept to trigger, to decode a 7-segment display from a decade counter. So now I've attached a low frequency oscillator to be the clocking circuit, the clocking signal for the CD4017 timer. And here it is in an automated way, just counting away. And once again, I reversed the count. So in this way, the core rope memory works in any way you set it, but it's hardwired. And so I will leave you guys, as always, with the schematic of this particular circuit. Thanks for watching. Next time I'm going to try to use this for a real audio circuit, like a drum machine sequencer. So stay tuned.